Hi, I'm Jeske, and today I'm presenting my work on finding smart contract vulnerabilities using ConCert property-based testing framework, together with Mikkel, Daniel, and Bas. Smart contracts have gained massive popularity since first introduced in blockchains, and nowadays the majority of blockchains have some sort of smart contracts. They are used for financial transactions and many other use cases involving money. And since they are just software, there's also vulnerabilities just as any other software. We have seen countless of examples of smart contracts being exploited due to vulnerabilities and millions of dollars being lost. An analysis by Chainalysis showed that more than $3 billion of cryptocurrency assets were stolen in 2021, and the majority of them were related to DeFi and smart contract vulnerabilities being exploited. It also showed that the amount of money being lost due to vulnerabilities is heavily increasing year after year. This is, of course, not good, and this means that we should get better methods at preventing bugs from ending up in production code. There are, of course, many approaches to this, such as traditional unit testing and integration testing, all the way to formal methods such as model checking and formalification. In this work, we take the approach of property-based testing, which is similar to fuzzing and unit testing, in which you define some property of a program and then you generate vast amount of random inputs to that program and test if the property holds on all of them. This allows the user to spend more time thinking about the properties that they want to prove, instead of having to think about interesting cases to test the program on. It also allows us to cover a large space, a large part of the state space, without having to write manual tests for every single input. In this work, we primarily focus on functional smart contracts, and the methodology works for any smart contract language with accounts and message passing. We do this in CoC because CoC facilitates both testing and proving properties in one language, meaning that can first state properties and test them, and then later, once we are confident that the code is stable and that the property holds, then we can prove them using CoC's formal verification tools. Another benefit is that we can also cover multiple blockchains and smart contract languages in one tool. To do this, we use ConCert, which is an abstract model of account-based blockchain execution and smart contract formalization written in CoC. It allows developers to implement, test, and verify smart contracts all inside CoC, and then later extract the code to different blockchains and smart contracts languages using verified code extraction. As shown in the diagram, all of ConCert is implemented inside of CoC, including the smart contracts, the proofs, the property-based testing, the execution layer, and the verified erasure and optimization used in extraction. Extraction is done using the MetaCoC project, and this allows us to have verified extraction to several different languages, such as Camel-Ego and Liquidity, Elm, and Rust. Since contracts are implemented in CoC, they have to be pure functions. And this is also the approach that is used by many functional smart contract languages. This means that they become pure functions transforming the state, and as such, a smart contract is represented by two functions, an init and a receive function. The init function taking some context and some initial variables and producing as beginning a first state for the contract, which is called when the contract is deployed. The receive function, on the other hand, is called every single time that the contract is called, and it takes some context, the current state, and some message, and it produces a new state which replaces the old state and a list of actions Such actions can be calls, transfers, calls to itself, other contracts, and deployments of contracts. And these are all handled by a scheduler. Both the scheduler and the execution model is fully formalized in COG, which means that we can capture the execution in the execution traces, in this case, in the chain trace relation, which is a reflexive transitive closure of the proof relevant chain step relation. And the chain step relation represents a single action, such as executing a contract call, updating the block, updating account balances, deploying a contract, and so on. We contribute to the ConCert framework by extending the property-based testing functionality of ConCert. We do this by both extending the types of properties that can be proven and also by giving improvements to usability of the testing framework. We show the usability of the testing framework by giving 3 case studies, 2 case studies of real-world code contracts that rediscover known bugs in the iToken and the Dexter contracts, which are contracts on the Ethereum and Tezos blockchain. And we also give a case study finding new bugs in the basic attention token contract. This shows that the smart contract verification and testing framework in ConCert allows for finding bugs early and helps verification efforts by allowing you to both test and verify the same property. It gives a cost-effective and semi-automated approach to discovering bugs, which is lightweight and can be easily integrated into a development cycle of smart contracts, allowing you to get quick feedback while writing smart contracts. Besides the 3 case studies mentioned already, we also have other case studies from previous publications showing the testing framework and verification parts of ConCert. The testing framework is built on the QuickCheck library for COG. It is a library that provides property-based testing functionality for COG, and it's a re-implementation of the QuickCheck library for Haskell inside of COG. It allows generating data and testing that data on properties. So the way QuickCheck works is that you give it a generator for data and you give it a testable property. And it will then generate by default 10,000 inputs using that generator and test the property on every single one. If every single one passes, then QuickCheck will say that the property holds. If one of them fails, then it will return that one as a counterexample. We then extend this by adding generators and properties specific for blockchain and smart contracts. The most important of them being the blockchain chain trace generator, which generates execution traces of smart contract calls. This allows us to test many interesting properties, for example, inciting smart contracts. As a user, to use this library, you would provide 4 things. You'd provide an initial blockchain setup, which is the initial account balances of deployed contracts, or you could provide a generator for generating initial blockchain setups. You would also provide a generator for contract calls for the contract that you want to test. And you'd provide a show instance for contract types, which tells QuickCheck how to print your types, which is needed to show the counterexamples. These show instances can almost always be generated automatically using QuickCheck and ConCert. And then finally, you would need a testable property. In QuickCheck, a testable property is just any decidable property inside of COG. And since we have full formalization of the execution layer and execution traces, we can test a lot of interesting properties. For example, we can test functional correctness, such as horse-style pre-post conditions of single contract calls. We used, for example, this in the iToken case study to show a bug where users could mint tokens without permission. due to a misplacement of a single line inside of a contract. We can also test temporal properties, and this is used heavily in BAT token, basic attention token case study. We can test things like reachability of states and evolution of contract state over an execution trace. Finally, we can also test smart contract interactions between multiple contracts with itself, and this can show reentrancy bugs and execution order dependency bugs. For example, this is used in the Uniswap case study, which we have shown in previous publications, and the execution order dependency bug in the Dexter case study in this work. And basically, it showed that a known bug in the Dexter implementation where the bug was only present in breadth first execution order and not in depth first. And this is one of the strengths of the testing framework here, is that you can test in many different execution orders and therefore cover several different blockchains and smart contracts. One interesting case study is the basic attention token smart contract. This is particularly interesting because it's the only case study in which we found new bugs which hadn't been covered before by anyone. And this was interesting because it's a smart contract which has been out there for a lot of years and have several audits on it. It's also the most extensive case study showing that you can actually find bugs without knowing them beforehand. The contract is an initial coin offering smart contract running on Ethereum, which means that it's a combination of a token contract and a crowd sale contract in the sense that it has some funding period in the beginning when it's deployed, where users can fund the project in return for tokens. When the funding then succeeds, the user keeps their tokens and the contract continues working as a standard ERC20 token contract. However, if funding should fail, then users can get their money back if the funding didn't happen. We tested a lot of properties for this smart contract, but in particular, these 5 properties were the most interesting. The first one stating that minting should only be possible during the funding period and not after. So when the funding is done, no more tokens should be able to be made. Also, we tested that funding should always be achievable. It should always be possible to get to a state where the contract is fully funded, given enough user engagement. Of course, if no one wants to fund the project, then of course it shouldn't be possible. Then we also tested that funds can't get frozen in the contract, which is a property you would always want for all contracts, because funds getting frozen is bad. It's just period. We also tested the refund guarantee because users are supposed to be able to get their money back, and the basic attention token actually came with a legal contract stating this. So of course users should be able to get their money back. And lastly, since the contract gives the owner some free tokens, those tokens should not be refundable, which is the last property we tested, or the last property of these. Of course, it's a bit bad if any of these properties don't hold. It turned out that only the first property holds, and the last 4 doesn't hold. So additionally, after testing, we proved that the first property actually holds. And after investigating the counterexamples given by the testing framework, we were able to fix the problems in a new implementation of the contract and show that this new fixed version that you actually could prove the properties for this new version. To be able to do these tests, we of course need to be able to generate calls to populate the execution traces. In general, Quick Check and ConCert can derive these generators automatically for most smart contracts. However, in most cases, if you have a smart contract that is just slightly complex, then these automatically derived generators are not that great. They generate too many inputs that are not interesting and cause the contract to fail, which means that it's harder to find vulnerabilities and you have to run a lot more examples to find vulnerabilities. So therefore, it's important to have good generators because the quality and speed of tests depends heavily on the quality of the generators. Luckily, it's often not that hard to build generators, and ConCert comes with a ton of built-in generators for common types and situations. And for most of the case studies, this has been a case of just writing glue code combining these built-in generators. One of the properties that we tested using this generator and this framework was the property that funding should always be possible. More specifically, that is that for any initial contract state, there should exist a trace that would lead to a state in which the contract is fully funded. To test this, we need two things. We need a generator for initial configurations of the contract, and we need a predicate telling, given a state, whether the contract is fully funded or not. And then we can combine these, as shown in the code on the slide, with built-in tools from the framework to come up with this test stating that for any setup generated by the setup generator, there should be a state which is reachable from the setup in which there is fully funded predicate holds. Running this test, we found that there were multiple different classes of setups which the contract would accept, but which would cause the contract to not be fundable. One example being that it doesn't check whether the starting block number and the ending block number create a non-empty range. So you could have deployed the contract with an empty range of blocks, which would mean the contract is completely useless. One of the slightly more interesting properties is the refund guarantee. And this basically means that if you donated and you still have the tokens when the funding fails, then you should be guaranteed to be able to get your money back. And we can state this in terms of stating if there's enough balance to refund everyone. And this basically is that for any state, the contract balance should be greater than or equal to the total amount of tokens minus the non-refundable tokens that the owner got divided by the token exchange rate. We can write this test up as follows, where the contract balance lower bound corresponds to the conjecture. Running this shows that the property doesn't hold, and we get the following counterexample, which shows that while the owner is not able to call the refund entry point himself, he can then instead call the transfer entry point and transfer his non-refundable tokens to someone else, and then they're suddenly refundable because the other user is not prevented from calling the entry point, which means that should funding fail, the owner can quickly call off this exploit and get all the money before any users can refund their money, which is not great. Luckily, the contract did succeed in funding when it was deployed, so this exploit couldn't have been carried out. But had this funding not succeeded, the owner could have done this. So in conclusion, we have shown that our property-based testing framework in ConCert helps finding bugs in real contracts and integrates well with formal verification in the sense that you can both test and verify the same properties in the same framework. We've shown that we can test functional properties, temporal properties, and contract interactions, and that the framework can find many of the most common types of vulnerabilities. And thank you for listening.